Campbell, we are back for part 2 of our discussion on dimensions.
Awesome.
Welcome back, everybody, to the question field. Of course, this is the place where you ask the questions and we field them. Part 1 of this conversation, that was in last episode, but maybe you're just feeling like you want to get thrown right in the middle, in which case we're going to get going and you'll be thrown right
good. In. You'll sink or swim.
Yeah. So, Campbell, I have a question. So I've heard, and so I've read a little bit about string theory in relation to all these dimensions, and a diagram I've seen before, a diagram I think I've seen on your website.
Oh my goodness. Oh no, you're holding me to account.
No, I've heard this in other places as well, or I've seen this. It's string theory. There are many extra dimensions, different numbers of extra dimensions, of spatial dimensions, I believe, depending on your particular brand of string theory. Some of them say that these spatial dimensions, so I guess for us, right, or for me, who is very well acquainted with the 3 dimensions that I appear to occupy, I'm curious where those extra dimensions would be. And so one of the diagrams I've seen is that those other spatial dimensions would be teeny tiny, and it would be almost as if I'm walking on the tightrope. Right? There's only one direction. I can go forwards and I can go backwards on the tightrope, and that's it, right? But if I have my little pet ant on the tightrope with me, right? Of course, the ant can go around the rope as well as going forwards and backwards. So
if you zoom in, it seems like there's this extra direction that you can move in.
Right. Who, what, where, why, and how?
Okay, right. So I guess the first thing we should say is that this is, in terms of modern theory, this kind of all fits within the framework of string theory. Strings are the reason that people are interested in extra dimensions for the most part.
And I'm sure at some point we will have an episode dedicated solely to...
Dedicated to string theory.
Yes.
Yeah, absolutely. And there are a couple of caveats. The first is, obviously, not everyone agrees with string theory being the right direction to go in for theoretical physics. The appeal of string theory is that it unifies, or it is an attempt to unify, Einstein's theory of gravity, which is called general relativity, with quantum theory. And quantum theory is the theory that describes the movement of microscopic particles, or bunches of them, or very, very energetic systems as well. Yeah. So if we can unify these 2 theories, which at the moment is very, very difficult, if we can unify them, then physicists tell us we'll have a theory of everything, something that describes all of fundamental physics.
And then our homework is complete. There's no more homework after the theory of everything. It's all there.
Right, textbooks end. Well, yes. So that's maybe perhaps the naive way of thinking about it. Of course, there'll always be more physics to do, but yeah. So that's the promise of string theory. It says we've got this theory which unifies gravity with quantum theory. And that is very exciting, but there are a lot of caveats with that. And those caveats are the reason that some people are very, very skeptical about string theory. And one of these caveats is that it can only work with extra dimensions. And so you ask where they are. Well, they are directions that you can move in that are perpendicular to all 3 of the directions that we know and love. So it's like if you were moving just in a plane, right, on a tabletop, there is an extra dimension that you could move in, and that is off the tabletop. Like, go back to the tightrope analogy. You're on a tightrope. You can only move in one direction, according to you. But from a different perspective, you could say, well, you're still moving in 3-dimensional space, right? You're just kind of restricted to move in one direction in 3D space. I'm trying to think of it another way.
We're just casually trying to define the extra dimensions of string theory. No biggie. It's not.
Obviously the easiest way to think about it is by not thinking about 10 or 9 dimensions, but actually thinking about 3 or 2 or 1.
I guess that idea of there being a restriction is compelling.
It doesn't seem too crazy.
I could buy that, yeah. Yeah. I could be sold that bridge.
It's kind of a constant theme of quantum physics. I think it's probably a theme of this podcast is that we'll be continuously saying there'll be an episode on this in the future. Right. There will certainly be an episode where we dive a bit more into quantum physics. But just to maybe extract the take home for this episode, there is a phenomenon in quantum physics, which is that if you place a restriction on a dimension, for example, so say, for example, you have a particle, it can move in 2 directions, right? one of those directions, it is completely free to move. While in the other direction, it has this wall. It has two walls, and those walls are very closely spaced. So it's sort of bouncing off those walls. What quantum theory tells us, there are only a certain number of allowed energies for this particle. The particle can't just have any energy, or actually maybe better to think about it in terms of momentum. Sorry, forget energy for now. The particle can only have a certain number of allowed momentum. And in the direction in which it's completely free to move, it can actually have any momentum. It can be moving at any speed in that direction. But the direction in which it's really constrained, so say it can move freely along the x-axis, but then if it tries to move along the y-axis, it hits one of these walls. So what quantum theory tells us is that the momentum in that extra dimension, in the y dimension, is what we call quantized. It can't take any value. It has to take either, for example, 0 or 10 kilograms meters per second,
right.
And then 20 and then 30 or something like that. So those momenta that it's allowed to have in that direction are spaced. They aren't continuous. They're only a discrete number that it can occupy.
Like the picture I have in my head is like a train terminal station, and you're only allowed on tracks 1, 3, 5, and 7.
Exactly.
Your bullet train can go any speed on 1, 3, 5, and 7.
Yes, that's exactly right. But you can only be on one of those tracks in the other direction. Yeah. So the analogy is that, or to stick with this analogy, if I move those walls closer together, so it becomes more and more constrained in that y direction, the spacing between those tracks gets bigger and bigger. So the allowed momenta it can have in that direction becomes more and more spaced apart. Another analogy, imagine that these allowed momenta are rungs on a ladder. So it can be traveling at 0 meters per second in this y direction, and that's like the bottom rung of the ladder. Then the next rung of the ladder is slightly faster, and then the next rung is slightly faster than that. And again, for all of these rungs of the ladder, it can be going any speed you like in the x direction. So the bullet train can be going at any speed, but you can only be on one of these tracks. If the walls of this system get moved close together, the rungs of the ladder get moved further apart. So the space between momenta in the y direction gets bigger and bigger.
Let me see if I got this. The more you squish your train tracks, the further the tracks will be from each other.
Yeah, that's basically right. Yeah. Which train track you're on is like which rung of the ladder you're on, which is how fast you're traveling in the y direction. The width of the train track is like the spacing of the walls, how constrained you are in that direction. If you are traveling in a space which is really squished in one direction, then it takes a lot of energy to travel at any speed in that direction, because it takes energy to travel with a certain momentum, and those momenta are spaced very far apart. So you can have 0 momentum in the y direction, in the direction perpendicular to the wall, but in order to have any non-zero momentum in that direction, you need a lot of energy.
Because you're putting a tighter constraint on the width of the track, we're saying, right?
Yep.
Like the train gets very focused and is very like, I can't touch the walls, man. I can't do it. And in order to, and it's just like kind of fritzing out like that means that it's harder to then make it to the next track up.
Exactly. Yeah. It's like it travels more and more in a straight line along the x direction. But if you move those walls further apart, then it can start to move in the y direction a little more.
It's vibing a little more.
Yeah, it can sort of oscillate a little bit. Yeah. If we think about these extra dimensions of string theory as being very, very constrained, like really, really, really tiny, you're going to need a huge amount of energy for a particle to move in that direction.
The conditions need to be so particular for them to access that. This is so hard. Maybe just unlikely that you get the perfect circumstances to get your particle to access that track, I guess?
Yeah, so that's exactly the right idea. It's really difficult to access these extra dimensions. But I think the thing we're missing here is that the thing that allows you to access that extra dimension is energy. So in string theory, if we have these extra dimensions, but they're really, really, really tiny, you could access those dimensions, but you would need a particle accelerator that creates huge energies. Like it would need to be the size of, I don't know, the galaxy or solar system or something like that.
Yeah.
So yeah, we're constrained to have zero momentum in those extra dimensions. So we can't access them, basically.
Right. The forbidden dimensions.
Yeah, that's right. We're talking about these walls as being the thing that constrains you to only have zero momentum in a particular direction. There is another way that you can have a constrained extra dimension, which you hinted at with the tightrope analogy. Do you know what that might be?
If they are self-contained?
Yeah, what do you mean by self-contained?
I feel like I'm cheating because I'm going off of things I think I read, but it seems like if
That's okay.
Well, I guess I can think about it in two ways, or maybe these are related. But if there are extra spatial dimensions, I don't see why they would necessarily have to be connected to other spatial dimensions. And I guess the follow-up, or maybe this is completely separate to that idea, is maybe they are some kind of looped space?
Yeah, absolutely. So the looped space idea is like the tightrope idea, right?
Yeah.
The extra dimension on the tightrope kind of curls back onto itself. It's a circle, whereas the large dimension of the tightrope is linear. It can go on for as long as you like. In terms of them like the direct dimensions all being interconnected, I guess the idea is that at any point in one of these dimensions, you can still access, you can still, in theory, move in the other dimension.
Yeah.
But yeah, so thinking about these dimensions as being like little circles is the generalization, or the way to talk about that in more fancy terminology, fancy language, is to say that these extra dimensions are compactified, which is quite a cool word. I like that.
Oh yeah, no, that's a killer word.
So maybe you can see why that might be analogous to if I had two walls that, are impenetrable and constrain movement in one direction.
Yeah.
It's sort of like you're constrained from moving in that dimension by the dimension itself, rather than from, by some external thing like a wall.
I guess the question that comes to me then from that is, how is that not essentially the same thing as being separate if it becomes something that's seemingly inaccessible?
Yeah, so really, really good question. Like, does this have any consequences on, say, physics on our three-dimensional universe, or three-dimensional plus time?
Right.
To rephrase what you're asking, do these extra dimensions have some sort of consequence for us in 3 dimensions of space and 1 dimension of time? Like, is there some physics that comes out of these extra dimensions?
Right.
And the answer is yes. And the question actually takes us back to, I think, 1916 or so, or maybe 17, with something called Kaluza-Klein theory. Have you heard about this, Brian?
Not even a little bit.
Great. Okay, perfect. Let me just make sure I'm getting the year right, because I want to paint the scene,
Sure, yeah, absolutely.
Okay, so 1919, not too far off. First World War's just ended.
Everybody's doing great.
Yeah. Yeah, the world's as good as it's ever been. Was he Swiss? I don't know. Einstein, anyway. That old guy has just recently published his paper on general relativity, right? Which is his theory of gravity. He's like a superstar now. And this guy called Kaluza, who I think was a bit of a weird guy.
So rare for the physicist to be a weird guy.
Yeah. I think he taught himself to swim by reading textbooks about it. He's a true theorist. Amazing. And then apparently he just dived in and was great. Anyway, so he sends a letter to Einstein saying, hey, I like your theory on general relativity. Have you ever thought about this? If you add an extra dimension to that, so you have now 5 dimensions of space-time, it turns out that you get electromagnetism for free. So what I mean is that one of the consequences of this extra dimension is that the electromagnetic force. And so, that's charges and magnets and all that. And I think Einstein kind of was like, no, this is a bit weird. But then maybe a bit later, and I'm probably bungling this history immensely, but I think a bit later he started thinking about this more seriously as a way to unify physics, because those were the only 2 forces they knew about at the time. We now know there are 2 extra, which are the weak and strong nuclear forces. But at the time, that it was just electromagnetism and gravity. And if you could unify those 2 together, you'd have this beautiful theory which encompasses all of physics.
You just got to find that extra spatial dimension. No big deal.
That's exactly right. And so Oscar Klein comes along a bit later and says, well, if you think about this extra dimension as being sort of wrapped up on itself like a circle, you get some extra things for free. If you take quantum theory for granted, then, well, what you can do is you can identify the momentum in that direction with the charge of a particle. And so if I just say that the charge is given by the momentum in this extra dimension, and I tell you that this dimension is really small, well, what did we say that means about the momentum of the particle?
Is this in relation to the more squished you get, the further,
Yep.
The further your tracks get from each other?
That's exactly it.
The train is no longer vibing; it's on the fritz, and so it's very hard to get.
It can only travel straight.
Yes.
Yeah, that's exactly right. So if your extra dimension is really small, your momenta are what we call quantized. So it can only take certain discrete values. And if I tell you that that momentum is equal to what we'd call the charge of a particle, well, then the charge is also quantized. And that actually is what we observe in nature. We only observe particles with a certain quantized electric charge. Quarks can have a fraction of the charge of an electron, but basically we can think of the electron's charge as being the unit of electric charge. You can't have sort of half of that. So this would be a beautiful explanation for the fact that electric charge is quantized. And so this grew into Kaluza-Klein theory, which is that if you add an extra dimension, you get extra physics, if you like. And in this particular case, it was electromagnetism. There was a problem, though, because, as we said, you need stupendous amounts of energy to access really, really small extra dimensions, right? And in special relativity, energy is the same thing basically as mass. E equals mc squared is what I'm referring to here. So if you need a lot of energy to have a charged particle, right? Because in order for a particle to be charged, it needs to have momentum in this extra dimension, which means it needs to access the dimension, which means it needs to have a lot of energy. And if you equate that with the particle's mass, then
you just get black holes everywhere. And
yeah, it's really, really massive. It's huge masses of particles. So it doesn't really work. But this idea kind of was the germ that spawned into the extra dimensions of string theory. Thinking about what happens if you compactify those dimensions kind of grew out of this Kaluza-Klein program.
That's wild. That's crazy.
Yeah. So you can kind of think, well, we have extra forces, right? We have, as I mentioned, you have the weak and strong nuclear forces. Are you familiar with these concepts?
Well, the strong nuclear force is what keeps our nuclei from doing bad things.
Yeah, it holds the nucleus of atoms together. The weak force is responsible for radioactivity. So it's a bit weird to think about. It's maybe not so intuitive as strong force is, it prevents the nucleus of atoms from flying apart. The weak force kind of results in beta particles getting spat out from atoms. It's a bit less intuitive to think about. But anyway, it's another one of the fundamental forces that we have. So we've got gravity, electromagnetism, weak and strong, four of them. And I'm sure we will go further into details on all of that in another episode. But so we can think about, could there be some number of extra dimensions and some way of compactifying those extra dimensions that gives us those forces that from our, say, 4D space-time perspective is the same as having these force fields that we know and love. That's part of what some people are interested in with string theory and these extra dimensions. String theory tells us that we need these extra dimensions in order for string theory to be consistent. And if you take that seriously, as many people do, some people don't, if you take that seriously, then you say, well, we need to compactify those dimensions because we don't see them, we don't observe them, so they need to be really, really small. And the way that you compactify those dimensions can influence the physics you see on large distance scales, like on our 4D perspective. It's a pretty crazy idea.
Yeah, no, my intuition would say if they're basically inaccessible, it would be hard to just be like, well, you could have as many extra dimensions as you want, but to know that there could be consequences that still result from this is kind of like, it's intriguing.
It's pretty crazy, right?
Yeah.
We could go a whole bunch of different directions from here in terms of this discussion, but maybe the reason, just to quickly say, the reason that you can't have extra, like the reason that string theory gives you the number of dimensions that you need is because of symmetry. So symmetry is really important in physics, particularly when you get into this sort of fundamental physics. I'm sure we can talk about this a bit further in some other episodes. So maybe if the listeners are interested in this, they can write in and we'll discuss it. But in any sort of quantum theory, particularly for these forces and particles that are able to access really high energies, you start with a classical theory. A classical theory is just one without the quantum stuff. And in classical theories, particles can only move along one trajectory. You know, if I give you the initial velocity and position of a particle, then you know how it's going to move through time, like how it's going to move.
Okay, I can play the tape backwards and forwards.
Yeah, that's exactly right. Whereas in quantum theory, if I tell you the starting position to predict, say, for example, the probability it will end up at that final position, you need to add up the probabilities that it went along all possible trajectories. So that's really weird. And so if you translate that to string theory, so string theory is a theory of strings. Instead of particles, you have little loops or strands of string. And you have to add up the probability that it starts at one configuration and location and ends at another. The classical theory of string theory has this really, really important symmetry, which is basically like you can stretch the rulers and the clocks that we use to measure space-time.
It turns into a Dali painting.
Yeah, that's it. Yeah, so you can turn a nice classical painting into a Dali painting, and the physics should be the same. Like we should all still. It's like that. I think from last episode we were talking about pens and a space-time interval as being something that everyone agrees on. So you should be able to stretch and squish your rulers in space-time, and everyone should agree on, and nothing should change. Like you should still be able to work your theory properly. And I'm being very, very hand-wavy about this. There,
listeners, his hands right now are unbelievable.
But that's the basic idea. This is a symmetry called Weyl symmetry or Weyl invariance, Weyl, named after Herman Weyl, I think.
My boy Hermie, yeah.
Yeah. And that's the symmetry of the classical theory, right? As in every point along the trajectory of a string has that symmetry. But in the quantum theory, you need to consider all possible trajectories. What that often means for the quantum theory is that some of these symmetries are broken. It turns out in string theory, you really, really need that symmetry to be preserved. Whether or not it's broken depends on the dimensions that you have. So it can only be preserved if you move in 10 dimensions of space-time, with some caveats. Right. but that's the basic idea. Like it's not consistent because the symmetry is broken if string theory is considered in different dimensions. So it needs to be 10.
Wow. Yeah. I'm sure there's lots of math that
it gets a bit hairy.
Points all that out. Yeah.
There was something else that I feel like maybe just to bring it down to earth a little bit more and also connect it to what we were talking about last time. The take home of this episode is, as we've mentioned a couple of times, if you have a direction which is really, really small, then it's difficult to access that direction, that dimension. There are a few ways that this plays out in more conventional quantum systems. Firstly, if we think about a molecule, right? You were talking last time about degrees of freedom and dimensions. If I think about a molecule which is just two atoms, right? Two atoms separated from one another. There are several degrees of freedom that molecule has, right? Do you remember like what those would be?
They were translational kind of, and then also rotational. And isn't there also just like the one that's like the real mover, or they could both be moving?
Right. So you're talking about like the bond length changing.
Right.
Is that right?
Yeah, like it can be compressing and expanding, and
that's it.
Maybe one has more influence, or
your your atoms could be kind of vibrating against each other. Yeah, so it's a vibrational degree of freedom. Thinking about the rotational ones, again, if I take my pen from last time, if I imagine that the ends of my pen contain the atoms in my molecule, right? So the atoms are located at the ends of the pen. I can spin my pen horizontally, right? So in a flat plane, or I can spin my pen vertically like that. Yeah. There's also another way that I could spin it, which is just to rotate the pen around its axis. Right. Yeah. I'm hoping that without these visuals that I'm doing right now, the listeners will still be able to understand what I'm talking about. You can like flip your pen around as if you're doing a trick, or you can just roll it between your hands, right? And it just turns around on its axis. There is some sense, right, in which that last rotation is kind of smaller.
Yeah, it's definitely not as it's not trying to show off like the other.
Yeah, that's right. Yeah, the if you're doing a pen trick, that's much more dramatic, right, than if you're just rolling the pen between your fingers.
You're leading the parade with your baton, and you know, one person is throwing their baton in the air and the other is twirling it very fast, and then there's just the one person at the end who's just rolling it. Yeah.
I think that guy would be kicked out of the band pretty quick. So this idea, this take home that we're getting at for this episode actually applies to this system as well. Because this degree of freedom is kind of small, it's less dramatic. To be a bit more technical about it, we can say that the moment of inertia about this axis is really small, whereas the moment of inertia around other axes is really large. But it's just less dramatic. Yeah. So that means that degree of freedom is difficult to access.
It is the introvert of the degrees of freedom, and much like myself, an introvert, hard to access. Right.
That's exactly right. Yeah.
Right. Okay.
I'm also a bit of an introvert myself, but sort of a bit easier to access, I think. Anyway. But yes, that's exactly right. It is sort of less dramatic, less flary, and harder to access. So when you're doing the degree of freedom counting, that degree of freedom, which only rotates it around the axis of the bond, that really introverted degree of freedom, you don't actually count it because it takes too much energy to access.
Okay. Yeah.
So, I guess this leads to a philosophical question, which is, there is that degree of freedom there in theory, but in order to access it, in order to excite some rotation in that direction, you need a huge amount of energy. And say, for example, I don't know if this is true for any molecule, I'm sure it might be for some. If you tried to give that molecule that amount of energy to excite that rotation, it would fly apart. It would it would sort of disintegrate. So is that really a degree of freedom? Like, is that an actual way in which it can move, or is it non-existent, you know? And similarly, if these extra dimensions are inaccessible, like say they don't produce any extra physics and they are truly inaccessible, like the amount of energy you'd need to access them would create a black hole or something like that.
Right, yeah.
Do they really exist?
Where do you come down?
I don't know. I think I'm more a balance between the two. Like, I think that there is a way in which you can think of unobservable things as existing if they have, if they, like in string theory, if they are important for consistency reasons. But also, I do think that you need to be a bit careful about making sure certain things have observable consequences.
If your molecule is vibrating in a forest and there's not enough energy to make
That's right. Yeah.
So Campbell, my brain is thoroughly mixed and it's thoroughly mushed. But listen, here's the thing, right? You're half the world away. I'm 12 hours behind you. So give me 12 hours and I'll be exactly on the same page as you. I just need that time
You'll
to
have done
process.
your homework.
Yes. No, thank you as always, Campbell. Thank you as always to our listeners. This has been part 2 of our first real deal episode, and we hope you stick around for many, many, many more and see me continue to make a fool of myself and hear Campbell try and pull me out of this whirlpool of physics that is currently trying to pull me under.
And if you have any questions about this topic, or if you have some other burning questions that you feel like, I don't know, are difficult to answer from a quick Google search or something like that, we'll write in and we'll do what we can to answer them.
Campbell will do what he can.
Or field them.
I will. Yeah. But I think that's all for now. Thank you so much, everyone. We will catch you next time on Question Field. I almost said the Question Field. had to fall back.
You've been listening to Question Field. Question Field is a Gain Media production and is produced by its hosts Campbell McLaughlin and Brian Buchanan. For more information, please check us out on Instagram at QuestionFieldPod, on Twitter at QuestFieldPod, and on TikTok at QuestionField. If you have a question you'd like to submit, or would simply like to leave a message, please send us an email at questionfieldpod@gmail.com. Recently, the James Webb Telescope discovered 5 new stars, located in the review section of your favorite podcast app. Thank you for listening.